All right, our next speaker is Guillaume Bornet. He's a postdoc with Jeff Thompson at Princeton, and he's going to talk about logical qubit circuits with Erasure.
Thank you. Thank you for the introduction. Can you hear me?
Yeah.
Yeah, good. Okay. Yeah. So thank you for the introduction. Yes, I would like to thank the organizer for giving me the opportunity for being here. And yes, today I'm going to present you our most recent work, which is about like the design of quantum computing with erasure error conversion. So, just as a reminder, just to give a bit of context, our platform is based on neutral atom array that we trap in array of optical tweezers. So these platforms are really common for many different quantum stuff applications. And so the reason why is that because we have a relatively good control over these atoms that we trap in these optical tweezers. So we can like encode the qubit states in all these different electronical levels, and we have a good coherence over these qubits. Moreover, these platforms are really scalable, and we can reconfigure like the array in nearly arbitrary geometries. And third, we can use this Rydberg-Rydberg interaction to entangle the atoms and make them interact. So let me give a bit more detail about this platform. So it's just a reminder. So usually the first step for this platform is to create a magneto-optic trap, which is just a reservoir of cold atoms that we use to load the optical tweezers. And so to create the optical tweezers, we use red detuned light that we focus inside the vacuum chamber. So in our case, we are using a microscope objective here. And so thanks to the light dipole interaction, at the focal point of this laser beam, one atom will see just an attractive potential. And if they are cold enough, they can be trapped in this optical potential. And so, of course, we want to create more than one tweezer because we want to play with more than one atom. And so what we do is that to create more than one tweezer, we use usually holographic techniques. And so we usually use like a spatial light modulator that I will refer as a SLM, which is used basically to diffract the light in such a way that when we focus the light inside the vacuum chamber, we focus the light on different multiple spots, and each of these spots are one optical tweezer for to trap one individual atoms. And so here, for example, you have an example of the typical geometry that we can do. So we can vary the distance between the atoms, usually between like a few micrometer to tens of micrometer, and we can have nearly arbitrary geometry. So for example, 1D, 2D, and up to some extent, we can go to 3D. Of course, one of the advantages of these platforms, as I said, is the scalability. And so there is, for example, this beautiful work from the Manuel Andres group in Caltech, where they showed that they can have up to 6,000 optical tweezers, which is a very good news for the future of these platforms. Another very important tool that has been developed with this platform is the ability to move the atom from one SLM trap to another SLM trap. And so to do so, we use acousto-optic deflectors. And so we use them to create dynamical trap, dynamical in a sense that we can like spatially move these traps. And the idea is like to superimpose the SLM traps with the trap generated by these IODs. And by doing so, we can move the atom from one SLM trap to another. And so with that technique, we can, for example, create defect-free array. So here at the top, you have an example with just a 1D chain. So the idea is that you first take a first picture to know which SLM trap contains or not one atom. And so once it's done, you know which atom to move to which trap, and you can move them using these IODs. And so here you see that the second line, you have a perfect 1D line, a defect-free 1D line. So of course, you can do that in 1D, but you can also do that in 2D. So people have shown in the past that now you can have like defect-free array up to 100 atoms. Julia showed us that, for example, yesterday. And I would like also to mention another work from the Gerwepan groups where they show that now you can get rid of these IODs and you can directly move the SLM trap to your target position. And so they show that using this fast spatial light modulator, you can kind of do the same work. And so this, I believe, is very interesting for the future of this platform because it's going to open new opportunities. Okay, so far we are just playing with atom in the ground state, okay, so nothing very fancy is happening. So now, if you want to make interesting quantum physics, you need to turn on interaction between the atoms. And so to do that, we are using Rydberg states. So I'm sure like most of you are very familiar with Rydberg states, but just for remembering, for the sake of remembering, so Rydberg states is just a very excited state with a principal quantum number, usually between 50 and 100. And so classically, we represent this Rydberg state where you have like just one electron orbiting very far away from the core and from the rest of the electronic cloud. And so because of that, this Rydberg atom will exhibit a very large dipole element. And so now, if you take like two atoms in the Rydberg state, usually separated by a few micrometers, they will exhibit an interaction strength of a few megahertz. And so this interaction strength, which leads to a dynamical timescale of a few microseconds, has to be compared to the lifetime of your Rydberg state, which is about a few, like 100 of microseconds. And so it means that you have the time to see your dynamics before having to face a decoherence effect from the finite lifetime of the Rydberg. So what kind of interaction do we have using this Rydberg-Rydberg interaction? So there are dipole-dipole interaction, and usually we use like off-resonant dipole-dipole interaction, also known as van der Waals interaction. So here, for example, you have an example, the energy spectrum of two nearby atoms. So the first state is a state with both atoms in the ground state. The second state is a state with one of the atoms in the excited state. And the last state is both of the atoms in the Rydberg state. And so as you can see, because of this van der Waals interaction, there is a shift associated to this state, which scales as 1/6. So this is this van der Waals shift. And so now, for example, assuming that you start with both of your atoms in the ground state, if you want to excite them to the Rydberg state, so you're just going to turn on your laser on resonance between the ground and Rydberg transition. And if your Rabi frequency of your laser is lower than this van der Waals shift, basically you won't be able, because it's off resonance, you won't be able to excite the atom to the two atoms to the Rydberg state, and you will only create a superposition of two states with only one of the atoms excited to the Rydberg state. And so this coherent superposition is an entangled state, okay? This mechanism is called the blockade mechanism, the Rydberg blockade mechanism, and this is the main mechanism that we use usually to entangle the atoms and to perform all these logical qubit gates. Okay, so just we take a step back. Okay, now we know how to entangle the atoms, we know how to move the atoms and so on. And so if we combine all these different techniques, you can do a lot of different like quantum experiments, and they all fall in mainly three categories. The first one is quantum simulation. So usually people, they study like using these interactions, they study like spin models. So the most famous example is the study of Ising model using this Rydberg, this van der Waals interaction. The second field is quantum metrology. So people can just, for example, like using this interaction, like engineer states that allows you to enhance the precision of your measurement. So for example, generating spin squeeze states. And the last category on which I'm going to focus my talk is, of course, quantum computing. So we had a very nice example with Julia's talk yesterday. Okay, so this is the outline of my talk. So let me just first talk about the specifics of our platform. Then let me show you a few examples of erasure error conversion for quantum computing. And at the end, let me just present you our most recent work about improving mid-circuit movement. Okay, so let's start with the unique features of our platform. So back in 2010, most of this atomic array platform they were using alkali atoms, so mainly rubidium and cesium. And the reason why is that because you have only one electron on the outer shell. And so what it means is that you have a relatively easy electronic structure, and so it's relatively convenient and easy to play with these atoms. This is why they started with these atoms. So later, a set of efforts have been made to trying to just expand the species that we can use for this atomic array platforms. And so now people are trying to play with these alkaline earth-like atoms, so mainly with strontium and ytterbium. And so because now you have two electrons on the valence bond level, the electronic levels, just the electronic levels are just richer, and it offers us like a new unique opportunities and new features. So I will just give you an example of this feature in just 1 minute. I just would like to mention that mainly, like, we are using two species, strontium and ytterbium. So for strontium, you have like the group in Manuel Andres and in Caltech, and the group of Adam Kaufman in Gila using this species. So it's mainly common for optical clock, but you can also use it for doing quantum simulation and quantum computing. And for ytterbium, so the pioneer work has been like led by the Thomson group, and most recently joined by the Kaufman group in Gila. So let's come back to the advantages of using ytterbium. So if you want to understand what are the advantages of using ytterbium, you can compare the ytterbium atoms with just an alkali atom, for example, rubidium. So for an alkali atom, you need to encode your qubit state in the ground state, so as it is showed here. And so now if you want to excite your atom to the Rydberg state, you have two choices. The first one is just a single photon transition directly to the Rydberg state. But if you want to do that, you need to use deep UV, usually less than 300 nanometer. And moreover, the dipole matrix element is very weak, so you need like a deep UV laser with a really high power. So as an experimentalist, you know that usually it's not a very good news. So usually what people do is that they use a two-photon transition using this intermediate state E. But the main issue is that usually this intermediate state has like a short lifetime. So if you want to avoid like spontaneous emission, what you need to do is like to detune your laser with like putting an intermediate state, intermediate detuning, sorry. But the problem is that if you do that, of course, you will lower your effective ground Rydberg Rabi frequency, and this you don't really want to do that, so you need to have a kind of trade-off between the intermediate detuning that you choose and the Rabi frequency that you want. Now, let's compare that to just the electronic structure of the ytterbium. For the ytterbium, you don't necessarily need to encode your qubit state in the ground state. You can use, for example, the metastable state, the 3p0, which historically is known to be like this 1s0, 3p0 is known to be like the optical clock transition for the ytterbium. And so starting with this metastable state, you just have like a single photon transition to excite the atom to the Rydberg state. The second advantage of this configuration is that while you're playing with the metastable state in the Rydberg state, the ground state is kind of free, and so you can do whatever you want in the ground state. So for example, what you can do is just image the ground state using this 1s0, 1p1 transition, while you're playing with the metastable state. And because the laser is off resonance, you won't have any effect, back action on the metastable state. And so this configuration is very appealing if you want to do like quantum erasure. So the idea is the following. For example, you can use with this metastable state, Rydberg state, to just, for example, to apply some kind of gates. But because of the relatively short lifetime of the Rydberg state, some of the atoms will spontaneously decay to the ground state. And so what you can do is that while you're driving your gate, you can continuously image the ground state, and you can detect if any atoms leaked into your ground state. And if it's the case, you can say, oh, okay, I see that there was an error, and you can you can do what we call erasure error conversion. Of course, you might also say, okay, but I don't have only spontaneous emission. For example, I can have black body radiation. And so the atoms, for example, they can leak somewhere else in the Rydberg manifold. And so we have this proposal to like excite, to ionize the Rydberg atoms, to ionize all these Rydberg states, and then to image this ion. And this would allow us to completely catch any erasure error and to completely like convert a large fraction of this leakage error. So that are the main advantages of the ytterbium. So let me try to give you an intuition of why quantum erasure is something that you want to do for quantum computing. So let's take, for example, a classical example with just a 5-bit repetition code. So let's say, for example, you have this 5-bit repetition code, so 50. If you want to decode this code, for example, you have some bit flip error, and so you will count the number of 0 and the number of 1, and if the number of 0 of 1 is higher than d minus 1 over 2, you won't be able to successfully decode your code. But now the story is different if you have some erasure error. If you if you are able to tell where are the errors, you just need like one bit, which is good, to be able to detect your code. And so that's the main advantage. And so now you can correct up to D-1 error. So that's the main advantage of this erasure error. And so you could wonder, okay, this is a classical example. What about a quantum example? It's a bit the same intuition. For example, people have shown theoretically that you can use, for example, this XZZX surface code. And you can, for example, design a code so that if you see an erasure error, you can replace the atom by a new one. And you can just measure the syndrome's atoms and correct for the errors. And if you do that, people expect that you can reduce your threshold error from 1% to approximately 4%. So it means that it's going to be less demanding for the experiment, but also if you can like decrease your error threshold, increase depending on how you see it, it means that you can reduce the ratio between logical qubits and increase the ratio between the number of logical qubits and the number of physical qubits that you need. And as we know, like scalability is one of the major challenges for quantum computing, and so it goes in the good direction. Okay, so this is the main motivation for why we want to do like quantum erasure conversion. So just let's present the experimental setup. So this is the experimental setup with just the metastable state and the Rydberg state. So we have a set of repumper and optical beam to just prepare the atoms from the ground state to the metastable state. It's not shown here. So once you are in the metastable state, you can drive, using a coil, you can drive transition between the two hyperfine level of the metastable states with a relatively large fidelity of more than 99.9%. You can also drive like just Rydberg excitation using this UV laser with like, so now we have a fidelity, two qubit gate fidelity of more than 99.4%. You can also image, do some non-destructive imaging of the atoms in the ground state using this green laser. And if you want to do quantum erasure, we have this destructive imaging using this 1S0, 1P0 transition that I mentioned to detect any leakage error from the Rydberg state. Okay. That's it for the specifics of our platform. So let's now just give you some flash out some of the work that we have done for erasure error conversion. So let's start simple with just like a single qubit gate experiments. So we just try, so we just apply just a randomized benchmarking with Clifford gate for this single qubit gate, and we just measure the fidelity as a function of the circuit depth. And so what we can do is that we can just, and so as you can see, we have like so we have a fidelity of 99.9, which is mainly limited by the lifetime of our metastable state, which itself is limited by the scattering, the Raman scattering from the light of the tweezer. And so now what you can do is that you can slightly change the circuit to add this mid-circuit detection, and you can just image the ground state. And so what you can do is that every time you see, you can just discard all the shots for which you see atoms in the ground state. And so if you do that, you can see that you can convert approximately 50% of your error. And so now the fidelity can go up to 99.6%. So this is just a relatively simple example to show you that erasure is very good for quantum computing. And we also measure that we have some 20% of losses in our model. Now you can do the same for a 2-qubit gate. So exactly the same thing. So now instead of having one atom, we have two atoms. So we are still apply randomized benchmarking, so we can measure the fidelity that we get. So in our case, it's 98%. And now you can apply this mid-circuit measurement, post-elect on this erasure error, and if you do that, you can increase the fidelity up to 98.7%. So once again, which shows you that this is very efficient. This error conversion is very efficient. Of course, you might say, okay, this 98 and 98.7% are relatively low fidelity compared to the standard that we can have now. So it turns out that we were limited by some kind of Forster resonance. And so Dr. Pepper and E. Lee in our group, they made some simulation and they find out that we were limited by this Forster resonance, and by choosing other Rydberg states, we could improve the fidelity up to 99.4%. Okay. So now what about like quantum computing? So one very, let's say, small code that we try to implement is this 422 code. So this code is ready with just a distance 2. So this code is too small to convert to correct any poly error, but you can detect any erasure. You can detect any error. And so what we do, this is just the code that we use to just prepare the logical qubit states, and we just add an extra qubit to detect any hook errors during the preparation of this code. And so what you can do is that at the end, you can just measure the output that you get. And in addition to that, you can add just a mid-circuit measurement to detect any leakage error. And so if you try to measure the outcome of this code, what you measure is that if you just measure on the parity, you see that you have an error of 2%. If now you just post-select all the shots on this flag qubit, you can decrease the error by approximately half. And so now if you just post-select on the parity the flag error and the erasure, you can decrease the fidelity, you can increase the fidelity, the end fidelity up to 0.05%, 0.5%. So another experiment that you can do is that you can just prepare this logical state, wait, and as a function of this waiting time, you can measure what the outcome that you get. And so as you can see, once again, if you apply this quantum erasure correction, you can see that you have a lifetime which is higher, and which once again shows that this quantum erasure code is very, techniques, are very useful. Of course, everything that I showed you before was just like post-selected, and you could wonder, is there a way to do it in a non-post-selected version? And the answer is yes. So now for this experiment, what we do is that we just decode we have this decoder, and we decode all the shots that we get. And so what you can see is that, so we decode with or without the erasure error. And so what you can see is that when we decode with the erasure error, we have a higher fidelity than if we decode without the erasure error. And so once again, this is an example of the fact that these erasure error conversions are really useful and are very promising for quantum computing. Okay, just I would like to flash out a few experiments that we have done. Also, we are trying to design like circuit that can handle like leakage errors. So that's something that we are working on. We are also thinking about doing some soft decoding, trying to use all the information that we have from this mid-circuit measurement. And we are also still working on the improvement of the gate fidelity to go from 99.4% to 99.9% and even beyond. Okay, and so just to say that everything that is here is just, the paper is in progress. Okay, I would like to spend the rest of my time just discussing the last improvement that we have done for this mid-circuit movements. So as I said, like the ability to move the atom is very appealing because you can have a bigger connectivity between the atoms. You can perform parallel operations between the atoms, and you can enable the zone architecture that Julia told us about yesterday. So for example, you can have some readout region when you read out the state of the atoms, some storage region where you just like store and preserve your atoms in a coherent way, and some region where you just shine your Rydberg beam to entangle the atoms. And so in our case, this architecture is really simple. We just have a storage region here where we just store the atoms, and just a gate zone where we shine our Rydberg beam, which is the top row here, where we just like entangle pairs of atoms. And so this architecture relies on the fact that moving the atoms, you have a very good fidelity when you move the atoms, meaning that you don't lose the atoms while you move them, of course, but you also preserve the coherence. So to preserve the coherence, you need to care about mainly two things. You need to care about scalar light shifts. So for example, for scalar light shift, if you have an alkali atom, you will have some differential scalar light shift. So you need to take care of that. But in our case, because we use the same metastable state, because we encode our qubit state in the same hyperfine state, we don't have this issue. But we need to take care about vector light shifts. So vector light shift can arise, for example, when you have some non-linear polarized light. And the thing is that even if you have a perfectly polarized light, as you focus the light, you will have some region around like the focal point where the light is no longer linear, but it's a bit elliptical. And this can create some kind of effective magnetic field perpendicular to the longitudinal axis. And so you need to take care about the polarization of your beam, because depending on the polarization of your beam, in one case, this effective magnetic field will be like perpendicular to your like quantization axis generated by your coils. And in that case, the error will be just quadratic. It will be a second order effect. But in the other case, if your polarization is orthogonal, you will have this vector light shift will just linearly add up with your magnetic field coil, and so you will have just a first order effect. So for us, what we try to do is just like to probe the coherence of our metastable states, just for static atoms, for these two different configurations of polarization. And so what we see is that the results are relatively the same for both configurations, with a coherence time in the metastable state of a few hundreds of milliseconds. So this suggests that we are not limited too much by the vector light shift. But now the story is different if you try to move. So here what we do, we just like repeat this Ramsey sequence to measure the coherence. But in the meantime, we just move the atom from one trap to another. And when we do that, we just measure the fact that the coherence is very low. So here you have the coherence as a function of the number of one-way trip. Here what I call one-way trip is just the fact to move one atom from one trap to another. So two one-way trip is just one trip, and so on. We just one-way trip is like 2.6 milliseconds. And so the reason why we have that is because when we move the atoms, in order to combine your AOD traps and your SLM traps, we use a polarized beam splitter. And so the polarization of these two traps are not the same. And so now if you say that you have a small displacement, for example, a dy displacement between your AOD and your SLM, basically you will force the atom to like explore a region where the vectorial light shift is really high, and it will cause some decoherence. And actually we can measure this decoherence, we can scan this displacement dy, and so these are just a plot on the bottom right, and you can see that we can recover this vectorial light shift. We can just measure the phase that we accumulate during this Ramsey sequence, and you see that the phase that we accumulate is consistent with our theory. And so the solution to solve that is just like to make sure that we have the same polarization for the AOD and the SLM, and also make sure that these polarizations are both perpendicular to the magnetic field. So you still have some vectorial light shift, but now this time it's just a second order effect because these polarizations are perpendicular to the magnetic field. And if you do that, you can remeasure the coherence, and now this time you barely see any decoherence compared to stationary atoms, so which is very good. The last thing that I would like to mention is, okay, so this was for the coherence, but what about the losses? And so right now, as you can see, these are just the losses that we have as a function of the number of one-way trip. And we are dominated by these losses. You see that after like 10 one-way trip, we lose approximately like 10%. And so we are still currently investigating why we kind of lose so much. So we had managed to identify 3 sources of errors. The first one is photoionization induced by the traps. The second one is Raman scattering depumping the atoms. It's also due to the traps. And the last one is just unknown sources of heating. So you might say it's not very well identified, but we believe that maybe the FPGA that we are using to drive the AODs may have some noise. So it's something that we are still investigating, and we are still working on that. Okay. Let me jump to the conclusion. So I hope I managed to convince you that ytterbium atoms array are a very promising candidate for quantum computing. The fact that we can use this metastable state and we can like perform single photon transition and use this quantum erasure conversion techniques are really promising. We showed a few examples using single and 2 qubit gates, also with this 422 code. And right now, we are just trying to go towards better fidelities and explore new correction codes, for example, the CNL code and soft decoding and so on. And the last thing is that just if you try to do quantum computing and if you try to combine AODs and SLM, please be careful about your polarizations because it may induce some vector light shift that may decrease your coherence time. And okay. So thank you for your attention. We'll be happy to take some questions.
Thank you for a great talk.